Hi viewers, in this video I will show you how I tested the light dispersion of my LED headlight bulbs and how I installed the resistor with my rear LED turn signal bulbs.
Technically, using aftermarket LED headlight bulbs is prohibited on public roads in the United States and in Canada. But in reality, the LED headlight bulbs are sold in many auto parts stores, in performance shops, and also online. So I decided to test them. The reason was that the headlighting of my Honda Lizzo was far too weak compared with the majority of the other vehicles. I ordered two LED headlight bulb kits to evaluate the light beam patterns and the compatibility with the DRL resistors of my Canadian vehicle. Another thing to consider was the cooling system of the LED headlight bulbs. In the north of the United States and in Canada, where the temperate zone is a bit cooler or cold, I don't think the fan-based LED headlight bulbs are really required for my needs. One kit included two headlight bulbs with small CSP chips and fanless heatsinks. The other kit had two headlight bulbs with large TOB chips that are cooled with heatsinks and fans. The fanless kit included an instruction manual and a pair of gloves. But there was nothing included with the fan-based headlight bulb. Before going too far with the installation, I checked if they were lighting up properly when the high beams were turned on and also when the low beams were turned on. The old school signal lever in my vehicle was made with mechanical switches, so there was no CAN bus problem. Most newer vehicles equipped with CAN bus systems can detect light problems and trigger a fault message or cause flickering lights. In this case, installing wire harnesses with a decoder or resistors can usually solve the problem. I wanted to know more about the light distribution of some LED headlight bulbs, so I made my own tests. I began with a standard halogen headlight bulb. This is the kind of light that is projected on my test panel when the terminals are connected to energize the high beam filament. In this video clip, the terminals are connected to energize the low beam filament. Here, the filament shield is blocking the light going towards the lower side of the headlight assembly reflector. In this sequence, only the high beam terminals are connected, but all COB LEDs are lighting up. This way, the low beam lighting area is combined with the high beam lighting area to emit more light. It doesn't mean it is a better light emitting design. In the following sequence, the low beam terminals are connected, and only the low beam shield areas with COB LEDs are energized. The engineering of the shields is not very efficient, and it creates a strange butterfly light pattern on the back panel. In this other video clip, the high beam terminals are connected and only the high beam CSP LEDs are energized to produce a good dispersion of light, except for the central shadow stripe. In the next video, the low beam terminals are connected to the low beam CSP LEDs. The low beam shields are also used to reflect sunlight towards the central shadow stripe to better illuminate the upper side of the headlight assembly reflector. Here you can quickly compare the 6 different bulb light patterns that I filmed. In the following test, I am only interested in knowing the efficiency of a DRL resistor. So, to do it, I will energize the low beam filament and the low beam LEDs with a car battery without a DRL resistor and also with a DRL resistor connected in series. The luxmeter that is part of this multimeter is used to measure the illumination on a specific surface. The spacing between the bulbs and the light sensor was the same for the 6 measurements. During the halogen test, when the DRL resistor was connected, the beam filament generated an average of 404 by 10 lux. But when the connection was direct without resistor, the average reading was 1925 by 10 lux. Then I tested the low beam of the fan-based COB LED headlight bulb. The average intensity was 715 by 10 lux when the DRL resistor was connected, and 1124 by 10 lux when the connection was direct without resistor. This light was dimming well with the DRL resistor, maybe because the fan was adding a bit more resistance in the circuit. On the other hand, with the fanless CSP LED headlight bulb, the average result with the DRL resistor was 1480 by 10 lux. And the average without the resistor was 1670 by 10 lux. I used only one side of the low beam CSP chips, rotated at 45 degrees. However, in this case, the LEDs barely dimmed. Since I didn't find any law prohibiting the use of low beam lighting during daytime, I decided to try the LED lighting bulbs with the CSP chips. First, I placed the headlight assembly on the workbench and I removed the old headlight bulb. Each fanless headlight bulb was provided with a well-designed black locking ring. This is the bayonet locking system. I fitted the locking ring in the housing opening, then I secured it with the retaining spring. The dot cover was properly fitted around the locking ring collar to make sure the housing was well sealed. The locking system of the black ring was well engineered, so it was easy to insert and lock the new headlight bulb. Then I tested the low and the high beam lighting with the headlight bulbs installed in the headlight assemblies. Later, I adjusted them and I tested them on a secondary street to see if the low beams were well adjusted to avoid blinding the oncoming drivers. The primary results confirmed that the lighting was brighter, but it also showed that the lighting patterns were not as even as the halogen light patterns were. The second part of the project was to remove the rear light assemblies and replace the old bulbs with LED bulbs. The main wire harness connectors and the retaining nuts are hidden behind the trunk liners. First I unplugged this main connector, then I undid the retaining nuts. The bulbs can normally be replaced without removing the rear light assemblies, but to demonstrate this upgrade, it was better to show it on the workbench. These are three kinds of LED light bulbs I bought to replace the old light bulbs. This light bulb has two filaments, and one filament is used as stoplight. To avoid hyperflashing, I also used 6 ohm resistors to mimic the resistance of common light bulbs. These kinds of light bulb sockets are keyed, so there is no mistake that can occur when an LED light bulb is inserted. Here I show that this LED light bulb cannot be inserted if it's not fitted properly. This light bulb is made with a flat base, therefore it can be installed the wrong way because it's not keyed. If the light bulb doesn't light up, it should be tested the other way around. Next, the 6 ohm resistors had to be installed to mimic the normal circuit resistance. To identify the 12-volt signal coming from the turn signal wire, I used a simple 12-volt circuit tester while the flasher relay was active. The alligator clip must be connected on a known good ground point during the test. Usually, a resistor is installed in parallel between the two wires that energize an LED light bulb. In my installation, it was a bit different, but I obtained the same result. I used the chassis structure to secure the resistors. I also connected each ground return wire directly to the chassis structure. Here, I used the mirror to show how I fastened the resistor behind this side panel. Not long after, I refitted the rear light assemblies and I reconnected the wire harness connectors. Then I tested the rear lights. Hazard, markers, brake, reverse, turn left, and turn right. I was not satisfied with the LED brake lighting, so I replaced the bulbs with standard amber light bulbs.
LED lighting is now part of the automotive industry, but the maximum brightness of the headlights and some other lights should be regulated, as well as the Kelvin color temperature of the LED lights.